In this lecture, we're going to discuss the topic of homeostasis. By definition, homeostasis is maintaining a relatively stable internal environment despite continuous outside changes. Said another way, it's simply keeping the body in equilibrium in a state of balance. This has to do with a lot of different conditions inside the body. As you can imagine, the environment changes. It might change from very humid to dry. It might change from very hot to very cold. There might be stimuli on the body from the external environment. There are also changes that might occur on the inside. Maybe blood pressure goes up, or blood pressure goes down, or what about blood sugar? What if blood sugar gets too high? These all have to do with a concept called homeostasis. This concept is a consistent theme throughout AMP1 and AMP2. So we need to make sure we understand it completely and thoroughly now so we don't have to revisit the basic meaning of homeostasis. What we see here on the left is a good figure to think about when homeostasis is brought up. Homeostasis is typically started with an idea that there is some sort of stimulus. The stimulus could be an external stimulus on the body or an internal stimulus. But what we mean by a stimulus is a change in the condition, either an increase or a decrease of some condition in the body that needs to be tightly controlled. A good example is temperature. If the temperature in the body reaches too high, the body can be harmed. High temperature disrupts enzyme activity and how the body works. So we have to be able to monitor that controlled condition. In order to monitor a controlled condition, we use what's called receptors. Receptors are structures within the body, often attached to neurons, that can detect different internal conditions. An example of receptors that monitor temperature is thermoreceptors. The body has thermoreceptors in two primary locations. One is in the skin. The thermoreceptors of your skin are constantly monitoring the temperature in your surrounding environment. We also have thermoreceptors found in an area of the brain called the hypothalamus. The hypothalamus is a part of the brain that does a number of different things, but one is it consistently monitors your internal body temperature. It can also change that temperature. If we need to increase temperature in order to have a fever, the hypothalamus will do that. But let's keep it pretty simple here. We have receptors throughout the body that are monitoring controlled conditions. Those receptors have to send a signal to the control center, usually by way of nerve impulses or other chemicals. The control center is what interprets this information. So the control center receives and provides information regarding that condition. So the control center, usually your brain, assesses this information, determines what to do about that information, and signals what we call effectors. Effectors are the organs that can bring about a change. So if the temperature was really high, an effector must be some structure in the body that can help bring down body temperature. And if you think about that, when you're really, really hot, what does your body do? Your body sweats. And that sweat evaporates and extracts heat from the body. You also send more blood flow to your skin. That also helps remove heat from the body. So whatever the effectors do, we call that the response. So if you look at this, there's really 5 components of homeostasis. There's a stimulus, there's a receptor, there's a control center, There's an effector or effectors, and then there's a response. And if you think about what the response should be, it usually, not always, but usually is opposite the stimulus. So for example, if our stimulus was high body temperature, the response better be to lower that body temperature. If the stimulus was low body temperature, maybe we are very, very cold, the response should be to generate heat. For example, muscles will shiver in order to generate heat. So let's look at some other examples of homeostasis. We mentioned body temperature. We've probably heard of that number, 98.6 degrees Fahrenheit or 37 degrees Celsius. That's the controlled condition. If body temperature gets too high, that can be detrimental. If body temperature gets too low, that can be detrimental. So we need to keep it at roughly 98.6. We call that the set point. It can fluctuate, but we want to be fairly close to that 98.6 Fahrenheit. What's another example? Blood pressure. You've probably heard of these numbers before, 120/80. Millimeters mercury is just a unit of pressure. Just like Celsius and Fahrenheit is temperature, millimeters mercury is a unit of pressure. And that's the pressure in our arteries. We'll talk more about this in A&P2, but we need to maintain a relatively constant blood pressure. If it gets too high for too long, that can cause damage to organs like your brain and your kidneys. What's another example? Blood sugar. This is the normal range we should be at when we're fasting. Okay, now it'll go up after a meal, but we don't want it to stay high. We want to be able to bring it back down. If we've gone hours without a meal, our blood sugar will be low. We don't want it to get below 70, so there's got to be measures that are taken to keep it above 70. So 70 to 110 milligrams per deciliter is the amount of blood sugar or blood glucose you should have normally, and it's usually taken when you're fasting, when you haven't had a meal. Another example, pH. This is the pH of your blood, 7.35 to 7.45. We'll talk a little more about pH when we get to chemistry in the next unit. But that's the range that our blood should be. If it gets too high, that's not good. Enzymes don't work at that higher pH or a low pH. So we need to have measures in place to maintain blood pH. A lot of hormones are tightly monitored. A good example would be thyroid hormones. Thyroid hormones control your metabolism, and we don't want thyroid hormones to get really, really high. We don't want them to go too low. So we have to keep them in homeostasis. Oxygen and CO2 levels are tightly monitored. Too much or too little of each can be detrimental. Electrolytes, there's a whole host of electrolytes, sodium, potassium, calcium, chloride, all need to be monitored and maintained in certain levels. As you can imagine, your kidneys are very important in this. Your kidneys can get rid of some of these electrolytes if they're too high. Your kidneys will retain them if they're too low. Fluid levels. A lot of fluids in the body need to be regulated. There's intracellular, which is the fluid inside of your cells. There's interstitial, which is the fluid outside your cells or in between your cells. If we get too much interstitial fluid, there's a name for that. The name is edema. When there's a tissue that has edema, it swells, it's swollen. Blood plasma is the liquid part of your bloodstream. We're going to talk a lot about that in A&P2. You don't want too much fluid in your blood space. Lymph is a fluid in your lymphatics. We'll talk more about in A&P2. There's cerebral spinal fluid. This is fluid that surrounds your brain and spinal cord. We'll talk about that this semester when we get to the nervous system. Synovial fluid is found in a lot of your joints. It helps kind of cushion your joints. It helps lubricate your joints. It helps keep the cartilage of your joints healthy. And then there's some fluids that are found in your eyes. We'll get to eyes at the end of the semester, but there's a fluid called aqueous humor and vitreous body. Humor is a body fluid. So if you see that word anywhere, it just refers to a liquid in the body. So all these things are examples of controlled conditions in the body that are tightly monitored using receptors, a control center, and effectors. There's a couple ideas that I want to talk about that have to do with homeostasis. They're called feedback mechanisms. And there's negative feedback, and then there's positive feedback. Now notice these diagrams look a lot like the previous diagram that showed homeostasis. And they are. The difference is this is a specific controlled condition. Let's look at this first one on the left. The controlled condition we're looking at is blood pressure. That is the condition we need to keep in balance. The stimulus would be high or low. If blood pressure gets too high or blood pressure gets too low, we need to be able to monitor that, so we have receptors. These receptors happen to be called baroreceptors. Baro means pressure. So these are pressure sensors. You've got sensors in your body in certain blood vessels. They're located in your carotid arteries that are in your neck and the aorta that comes out of your heart. But we detect pressure there. And if it gets too high or low, we notify the brain. There's actually an area in the brain called the medulla oblongata that receives this information and determines what to do about it. So if blood pressure gets too high, your brain gets that information and notifies the effectors. The effectors are your heart and blood vessels. That should make sense. Blood pressure is due to your heart contracting and due to the pressure in your blood vessels. Those organs can bring that pressure down if it got too high, or they can bring it up if it got too low. And that would be the response. The response when the blood pressure is too high is your heart rate goes down and blood vessels dilate or widen. We call that vasodilation. So if your blood pressure gets dangerously high, your heart rate will go down and your blood vessels dilate. That relieves the pressure. So what do we mean by negative feedback then? The negative feedback is right here. Notice that the response is opposite what the stimulus was. Whenever the response is opposite, we call that a negative feedback. If the response was the same, it would be a positive feedback. Most systems in the body are controlled by negative feedback. So this mechanism here is much more common than this one over here. So let's look at a positive feedback. Positive feedback is when whatever that stimulus was needs to be reinforced. And it'll make sense when we look at this example of normal childbirth. The stimulus is contractions of the uterus which force the baby to the cervix. The cervix is where the baby has to come out. Okay, so in this little drawing, if you look closely, there's a baby, right, inside of a uterus. Here's how the baby needs to come out. Okay, there's an opening in the uterus called the cervix. That's going to lead to the vagina, and that's how the baby comes out. So the stimulus is stretching of that cervix because the baby is beginning to be forced out of the uterus. So if you think about that, and the whole idea here is to deliver a baby, you want to reinforce that. You want more of that uterine contraction to help push the baby out. So that's a positive feedback. The response is going to be more uterine contractions. So this happens towards the end of a pregnancy. We get uterine contractions. stretching of the cervix. The cervix actually detects that. It has what we call stretch-sensitive neurons. It knows when it's being stretched. So that's in essence telling that reproductive system it's time to deliver this baby. So there are nerve impulses from the cervix that go up to the brain and tell a part of the brain to signal more uterine contractions. How the brain does that is it produces a hormone. The hormone is called oxytocin. We'll learn that hormone in more detail in A&P2, but oxytocin stimulates more uterine contractions. We get more uterine contractions, that baby gets forced into the cervix more, and it stretches the cervix more. Think about what happened up here when we said the cervix stretches. You trigger more oxytocin. So what's going to happen is when that cervix stretches more and more, it signals a positive feedback to stimulate more oxytocin. So we call this reinforcement. We're going to not oppose that stimulus. We're going to reinforce it. We're going to do more and more of it. The goal here is to deliver the baby. So once that baby is born, the goal has been reached, and this process can stop. But notice the difference. We have a positive reinforcement versus a negative feedback. There aren't that many positive feedback mechanisms. This is the most common one used to describe positive feedback. There's also blood clotting. When blood starts to clot, you want to reinforce that so you can really form a solid blood clot to prevent bleeding. So we should look at this and be able to understand the difference between negative and positive feedback. These are just a couple really good examples to better understand the two processes. So that's our discussion on homeostasis. The next video is going to talk more about some regions within the body. We're going to get into cavities and where certain organs are found as well.